Numbers and numeration, a calm introduction to the foundations of quantity. Numbers and numeration, in their most basic essence, constitute the initial framework through which mathematics interprets the concept of quantity and order in the surrounding environment. This principle is explored gradually, beginning with the simplest forms of counting and extending into more structured systems that allow for representation and comparison of values. Natural numbers, which commence with 1 and proceed indefinitely, such as 1, 2, 3, and beyond, are employed primarily for the act of counting discrete objects, like tallying the leaves on a branch or the steps along a path. These numbers are introduced in a manner that emphasizes their sequential nature, where each subsequent number represents an increment of 1 unit from the previous, fostering an understanding that builds without urgency or complexity. The inclusion of 0 expands this set into whole numbers, where 0 serves as a neutral element, indicating the absence of quantity, much like an empty vessel that holds potential but no immediate content. 0 is positioned as the origin in numerical sequences, allowing for a balanced perspective on presence and absence. From this foundation, integers are formed by incorporating negative numbers, which extend the number line to the left of 0, representing concepts such as deficits or opposing directions. For instance, a temperature of -5 degrees or a descent of 3 units below a baseline. The number line itself is visualized as a straight, infinite path, with positives stretching to the right in ascending order and negatives mirroring this to the left, creating a symmetrical structure that invites contemplation of equilibrium. Place value emerges as a key organizational principle within numeration, where digits are assigned significance based on their position within a number. In the decimal system, which is based on powers of 10, the rightmost digit denotes ones, the next tens, then hundreds, and so forth. For example, the number 234 is decomposed passively into 2 hundreds, 3 tens, and 4 ones, illustrating how each position multiplies the digit by a power of 10, hundreds being 10 squared, tens 10 to the first, and ones 10 to the 0. This system allows for the representation of large quantities efficiently, without the need for excessive symbols, and it is applied in writing numerals that convey precise values, such as denoting a collection of 1,000 items with the compact form of 1,000. Comparisons among numbers are facilitated through relational symbols, where greater than, less than, or equal to are used to express order. A number like 7 is recognized as greater than 4 because it occupies a position further along the positive number line. An equality is noted when two quantities match exactly, such as 5 equaling 5. These comparisons are extended to sets, where the cardinality, or the total count, of elements in one group is matched against another, determining which has more, fewer, or the same amount. In early learning contexts, this is achieved through one-to-one correspondence, pairing items from two sets to observe any unpaired remnants, which indicate inequality in a straightforward, observable way. The concept of ordinal numbers complements cardinal numbers by focusing on position rather than sheer quantity. Ordinal numbers, such as first, second, third, describe the rank or order in a sequence, like identifying the third book on a shelf or the first day of a week. This distinction is maintained with care, ensuring that while cardinals answer how many, ordinals address in what position, providing a dual lens through which sequences can be viewed. Numeration systems beyond decimal are also considered, though at a beginner level they serve to highlight the arbitrary yet functional nature of bases. For instance, Binary uses base 2 with only zeros and ones, where positions represent powers of 2, 1, 2, 4, 8, and a number like 5 in decimal becomes 101 in binary, as 4 plus 1. Roman numerals offer another historical perspective on numeration, employing letters like I for 1, V for 5, X for 10, and so on, with rules for addition and subtraction. IV denoting 4 as 5 minus 1, while VI is 6 as 5 plus 1. This system, though less efficient for calculations, illustrates how different cultures have developed methods to record quantities, emphasizing subtractive notation for values just below key milestones. In contrast, the Hindu-Arabic system, which forms the basis of modern decimals, incorporates 0 as a placeholder, enabling the expression of any magnitude without ambiguity, a feature that revolutionized mathematical recording and computation over centuries. Rounding and estimation introduce approximation within numeration, where numbers are adjusted to the nearest multiple of 10, 100, or other units to simplify mental calculations. For a number like 47, rounding to the nearest 10 yields 50, as it is closer to 50 than to 40, guided by the rule that digits 5 and above prompt an increase in the preceding digit. This principle is applied in practical scenarios, such as estimating the total cost of items or the distance traveled, allowing for quick assessments without precise tallying. Scientific notation extends numeration for very large or small numbers, expressing them as a coefficient times a power of 10. For example, 3 million as 3 times 10 6, facilitating the handling of astronomical or microscopic scales in a compact form. Even and odd numbers are classified based on divisibility by 2. Evens like 2, 4, 6 leave no remainder when divided by 2, while odds like 1, 3, 5 do, creating patterns that recur in sequences and aid in recognizing parity. Multiples and factors further refine this, where multiples are products of a number and an integer, such as 10 being a multiple of 5, and factors are the integers that divide evenly, like 1, 2, 5, and 10 for 10 itself. Prime numbers which have exactly two distinct factors, one in themselves, such as 2, 3, 5, 7, stand out as the building blocks of all larger numbers through factorization, a process where composites are broken down, for instance, 12 as 2 times 2 times 3. In educational progression, these principles are internalized through repeated exposure, starting with rote counting and advancing to abstract representation. Children are encouraged to group objects into tens for base understanding, using manipulatives like blocks or beads to visualize place value, ensuring the concepts settle gradually into familiarity. The role of numeration in daily life is understated yet pervasive, from reading clocks to managing finances, where accurate representation prevents errors and promotes clarity. As one contemplates these foundations, the interconnectedness becomes apparent. Numbers not only quantify but also order the world, providing a stable reference amid variability. This exploration of numbers and numeration, though detailed, remains at the entry level, inviting further extension into operations and beyond. Each aspect connects seamlessly, forming a cohesive whole that supports all subsequent mathematical endeavors in a measured, unassuming way. Arithmetic operations, a methodical examination of fundamental calculations. Arithmetic operations, encompassing addition, subtraction, multiplication, and division, serve as the essential mechanisms through which quantities are manipulated and relationships between numbers are established in mathematics. These operations are introduced progressively, beginning with the most intuitive forms of combining and separating values, and extending into more structured rules that ensure consistency and predictability in computations. Addition, the process of uniting two or more quantities, is often visualized as the aggregation of sets, where a collection of three items merged with another of four results in a total of 7, represented symbolically as 3 plus 4 equals 7. This operation is grounded in the concept of accumulation, applicable to everyday scenarios such as tallying the pages read in a book over successive days, where 5 pages on one day added to 8 on the next yields 13 in sum. The commutative property of addition is observed, whereby the order of the addends does not influence the outcome, so that 2 plus 5 equals 5 plus 2, both amounting to 7, promoting a sense of flexibility in arrangement. Associativity further refines this, allowing for grouping in various ways without altering the result, as in 1 plus 2 plus 3 equaling 1 plus 2 plus 3, each equaling 6. The additive identity, embodied by 0, maintains that any number added to 0 remains unchanged, like 4 plus 0 equals 4, acting as a neutral element in the system. These properties are inherent to whole numbers and extend to integers, where addition of negatives equates to subtraction, such as 5 plus negative 3 resulting in 2, illustrating the balance between positive and negative forces. Subtraction, the inverse of addition, involves the removal or difference between quantities, where 8 minus 3 leaves 5, conceptualized as taking away 3 units from a starting set of 8. This operation is not commutative, as 3 minus 8 yields negative 5, distinct from 8 minus 3, highlighting the importance of order in the process. Nor is it associative, since 10 minus 4 minus 2 equals 4, while 10 minus 4 minus 2 equals 8, demonstrating how grouping affects the outcome. Subtraction is frequently employed to find differences, such as determining the variance in heights between two structures, where a tower of 15 meters subtracted from one of 20 leaves 5 meters as the disparity. Borrowing or regrouping is utilized in multi-digit subtraction, where if the minuend digit is smaller than the subtrahend, a unit is borrowed from the next higher place value, converting it into 10 units added to the current digit. For instance, in 42 minus 27, the 2 cannot subtract 7, so borrowing from the 4 tens makes it 3 tens and 12 ones, subtracting 7 from 12 to get 5, then 20 from 30 to get 10, resulting in 15 overall. This technique ensures calculations proceed smoothly across place values, maintaining accuracy in larger numbers. Multiplication emerges as an efficient extension of repeated addition, where 3 multiplied by 4 signifies 3 added 4 times or 4 added 3 times, both equaling 12. It scales quantities proportionally, such as finding the total apples in 5 baskets each containing 6, yielding 30 through multiplication. The commutative property applies here as well, with 4 times 5 equaling 5 times 4 at 20, and associativity permits regrouping, like 2 times 3 times 4 equaling 2 times 3 times 4, both 48. The multiplicative identity is 1, where any number times 1 remains itself, and 0 multiplied by anything results in 0, underscoring its absorbing nature. Distributivity links multiplication with addition, stating that multiplication over addition is equivalent to multiplying each addend separately and then summing, as in 3 times 4 plus 5 equals 3 times 4 plus 3 times 5, both 27. This property facilitates mental arithmetic and factoring, breaking down complex products into simpler components. In multi-digit multiplication, partial products are calculated, such as 23 times 4 involving 20 times 4 as 80 and 3 times 4 as 12, summing to 92, with place values shifted accordingly for higher multipliers. Division, the inverse of multiplication, partitions a quantity into equal parts, where 12 divided by 3 equals 4, indicating 4 units per each of 3 groups. It addresses sharing or grouping, such as distributing 18 candies among 6 children, resulting in 3 each. Division is neither commutative nor associative. 6 divided by 2 is 3, but 2 divided by 6 is 1/3, and 12 divided by 4 divided by 2 is 1.5, while 12 divided by 4 divided by 2 is 6. Remainders occur when division is not exact, like 13 divided by 4 equals 3 with one remainder, expressed as 3 1/4 in fractional form. Long division systematizes this for larger numbers, involving steps where the divisor is repeatedly subtracted from portions of the dividend, recording quotients and bringing down digits. For example, dividing 126 by 6. 6 into 12 goes twice, 12. Subtract to 0, bring down 6. 6 into 6 goes 1, subtract to 0, yielding 21. This method is applied methodically, ensuring each step aligns with place values. The order of operations provides a universal protocol for evaluating expressions with multiple operations, denoted by PEMDAS. Parentheses first, then exponents, multiplication and division from left to right, addition and subtraction similarly. An expression like 2 plus 3 times 4 is resolved by multiplying 3 by 4 to 12, then adding 2 for 14, whereas parentheses and 2 plus 3 times 4 yield 20. This hierarchy prevents ambiguity, ensuring consistent results across calculations. Properties extend to rational numbers, where addition of fractions requires common denominators, such as 1/2 plus 1/3 becoming 3/6 plus 2/6 equals 5/6. Subtraction follows similarly, while multiplication of fractions multiplies numerators and denominators directly, like 2/3 times 3/4 equals 6/12 or 1/2. Division inverts the second fraction and multiplies, as 1/2 divided by 1/3 becomes 1/2 times 3/1 equals 3/2. In decimals, operations align points for addition and subtraction, such as 1.23 plus 4.5 equaling 5.73 after aligning to 1.23 plus 4.5. Multiplication ignores points initially, then places based on total decimal digits, like 0.2 times 0.3 equals 0.06. Division moves points to make the divisor whole, adjusting the dividend accordingly. These operations interconnect, with multiplication and division as counterparts, addition and subtraction likewise, forming the bedrock for advanced mathematics. Applications abound quietly in budgeting, where incomes are added and expenses subtracted, in cooking, scaling recipes through multiplication, in sharing resources via division. Each operation, when performed with deliberation, reveals patterns and efficiencies, such as fact families where 3 plus 4 equals 7 implies 7 minus 4 equals 3. Arithmetic fosters problem solving, like determining unknowns in equations through inverse operations, subtracting to isolate in addition problems. Mental strategies enhance fluency, rounding for estimates or breaking numbers into friendly parts. Historical contexts note ancient systems like abacuses aiding calculations, evolving to modern calculators that automate but require understanding of principles. This examination of arithmetic operations, detailed yet accessible, underscores their role in quantifying the world methodically, each step a link in a chain of logical progression. Fractions and decimals, a steady exploration of parts and precision. Fractions and decimals, as fundamental components of mathematical representation, provide the means to express quantities that lie between whole numbers, capturing divisions of wholes into parts with meticulous accuracy. These concepts are developed methodically, commencing with the basic notion of sharing a single entity equally among a group, and progressing to more refined notations that accommodate infinite precision in measurements and calculations. A fraction is composed of a numerator positioned above a denominator, separated by a horizontal line, where the numerator indicates the number of parts selected, and the denominator specifies the total number of equal parts into which the whole is divided. For instance, 3/4 denotes 3 parts out of 4 equal segments of a pie, representing a portion less than the complete unit. Proper fractions are those where the numerator is smaller than the denominator, such as 1/2 or 2/5, always yielding values between 0 and 1, while improper fractions have numerators equal to or greater than denominators, like 5/4, which exceeds 1 and can be converted to a mixed number consisting of a whole and a proper fraction, such as 1 and 1/4. This conversion is achieved by dividing the numerator by the denominator to find the whole number quotient, and the remainder as the new numerator over the original denominator, ensuring the value remains unchanged, yet presented in a form that highlights the integer component. Equivalence among fractions is a key principle, where different representations express the same value, such as 2/4 equaling 1/2, determined by multiplying or dividing both numerator and denominator by the same non-zero number, like multiplying 1/2's parts by 2 to get 2/4. Simplification reduces fractions to their lowest terms by dividing both numerator and denominator by their greatest common divisor. For example, dividing 12/18 by 6 to yield 2/3, a process that streamlines calculations and comparisons without altering the inherent proportion. Common denominators are established for operations involving multiple fractions, found by identifying the least common multiple of the denominators, such as for 1/3 and 1/4, where 12 serves as the shared base, converting to 4/12 and 3/12 respectively. Addition of fractions with like denominators proceeds by summing the numerators while keeping the denominator constant, as in 2/5 plus 1/5 equals 3/5, extending to unlike denominators by first converting to equivalence, then adding as before. Subtraction mirrors addition, but involves deducting numerators after aligning denominators, such as 3/4 minus 1/6, where common denominator 12 allows 9/12 minus 2/12 to result in 7/12. Multiplication of fractions is executed by multiplying numerators together and denominators together, like 2/3 times 3/4 equaling 6/12, or 1/2 after simplification, conceptualizing this as taking a fraction of a fraction, such as half of 3/4 being 3/8. Division inverts the second fraction and multiplies, so 1/2 divided by 1/3 becomes 1/2 times 3/1, yielding 3/2, interpreted as how many thirds fit into 1/2. Reciprocals are the inverted forms of fractions, where the reciprocal of 2/3 is 3/2, and multiplying a fraction by its reciprocal always produces 1, the multiplicative identity. These operations extend to mixed numbers by first converting to improper fractions, performing the calculation, then reverting if needed, ensuring precision throughout. Fractions appear in practical contexts, such as dividing a recipe's ingredients by half or allocating shares of a budget, where 1/4 of $200 is 50, calculated as 200 times 1/4. Decimals transition from fractions by expressing parts in powers of 10, with a point separating whole numbers from tenths, hundredths, and beyond. For example, 0.5 equaling 5/10 or 1/2. Place values decrease by factors of 10 to the right of the decimal point. So in 2.34, 3 is 3/10 and 4 is 4/100. Equivalence with fractions is direct, where 0.25 equals 25/100 or 1/4, converted by writing the decimal as a fraction over the appropriate power of 10 and simplifying. Addition and subtraction of decimals require aligning the decimal points vertically, filling with zeros if necessary, then proceeding as with whole numbers, such as 1.2 plus 0.35, aligning to yield 1.55. Multiplication disregards points initially, multiplying as integers, then counting total decimal places to position the point in the product, like 0.4 times 0.5 equaling 0.20 or 0.2. Division shifts the decimal in the divisor to make it whole, moving the dividends point the same places, then dividing normally, as in 1.5 divided by 0.3 becoming 15 divided by 3 equals 5. Terminating decimals end after finite digits, like 0.25, while repeating one cycle indefinitely, such as 1/3 as 0.333, with a bar over the 3 to denote repetition. Conversion from fractions to decimals involves dividing numerator by denominator, where 1/7 yields 0.142857 repeating. Conversely, decimals to fractions place the digits over the power of 10 corresponding to places, simplifying, like 0.75 as 75/100 or 3/4. Rounding decimals approximates to specified places, looking at the next digit. If 5 or greater, increase the prior digit, else leave it, such as 2.37 to one place becoming 2.4. Estimation uses rounding for quick checks, like approximating 3.14 times 9.8 to 3 times 10 equals 30. Scientific applications rely on decimals for precision, such as pi approximated as 3.14159, enabling calculations in geometry and physics. Percentages bridge decimals and fractions, representing per hundred, so 50% is 0.5 or 1/2, converted by moving the decimal 2 places right and adding the symbol. Finding percentages involves multiplying, like 20% of 80 as 0.2 times 80 equals 16. Ratios akin to fractions compare parts, such as 2 to 3 or 2/3, extended to proportions where equal ratios solve unknowns, like if 2/3 equals x/9, then is 6 by cross-multiplying. Irrational numbers, like square root of 2 approximately 1.414, have non-terminating, non-repeating decimals, distinguishing them from rationals expressible as fractions. Operations with irrationals follow decimal rules, but often require approximation for practicality. Educational approaches introduce fractions through visuals like shaded regions or number lines, dividing a whole into parts and identifying selections, progressing to decimals with money, where dollars and cents naturally use tenths and hundredths. Activities involve cutting shapes or measuring lengths, reinforcing equivalence and operations in a tactile manner. This delve into fractions and decimals reveals their interplay, each offering a lens for partial quantities, interconnected with whole numbers and paving the way for advanced topics like algebra, where variables in fractions denote rates or proportions. Their utility in science, finance, and daily measurement underscores a quiet precision, allowing for nuanced expression of the world's divisions. Percentages and ratios, a balanced study of proportions and parts. Percentages and ratios, as interconnected principles in mathematics, offer a structured approach to expressing relationships between quantities, particularly in terms of proportions and parts relative to a whole, facilitating comparisons and calculations in a variety of contexts. These concepts are built upon the foundations of fractions and decimals, extending their utility to scenarios where relative sizes or scales are paramount, and they are introduced gradually to allow for a steady grasp of their implications. A ratio is fundamentally a comparison of two or more quantities, denoted by a colon or as a fraction, such as 2 to 3 or 2/3, indicating that for every 2 units of the first quantity, there are 3 units of the second, much like dividing a collection of 5 items into groups where one group has 2 and the other 3 to maintain the proportion. Ratios can be simplified by dividing each term by their greatest common divisor. For instance, reducing 4 to 6 by dividing both by 2 to yield 2 to 3, ensuring the relationship remains equivalent yet in its most basic form. Equivalent ratios are those that represent the same proportion, such as 1 to 2 being equal to 2 to 4 or 3 to 6, verified by cross-multiplying or scaling by the same factor, a process that preserves the balance between the terms. In practical terms, ratios are applied to mixtures, such as a recipe calling for flour to water in a 3-to-1 ratio, meaning 3 parts flour for every 1 part water, scalable to larger or smaller batches by multiplying each term accordingly, like 9 to 3 for a tripled amount. Unit rates derive from ratios by expressing them per single unit, such as a speed of 60 miles in 2 hours simplifying to 30 miles per hour, calculated by dividing the first quantity by the second, providing a standardized measure for comparisons across different scenarios. Proportions set 2 ratios equal to each other, forming an equation like 3/4 equals 6/8, solvable for unknowns by cross-multiplying. 3 times 8 equals 4 times 6, confirming 24 on both sides, or isolating the variable through algebraic means, such as if 2/5 equals x/10, then x equals 4 by multiplying both sides by 10 and dividing by 5, or recognizing the scaling factor of 2. Direct proportions occur when quantities increase or decrease together, like cost proportional to quantity where doubling items doubles price, while inverse proportions have one increasing as the other decreases, such as speed and time for a fixed distance where higher speed reduces time, expressed as x times y equals constant. These are graphed as straight lines through the origin for direct, or hyperbolas for inverse, allowing visual confirmation of the relationship. Ratios extend to 3 or more terms, like 1 to 2 to 3, meaning parts in that progression, useful in dividing resources among multiple parties, where a total of 6 parts allocates 1/6, 2/6, and 3/6 respectively. Percentages transform ratios into parts per hundred, denoted by the percent symbol, where 50% signifies 50 out of 100 or 1/2, converted from fractions by multiplying by 100, such as 1/4 times 100 equals 25%. Decimals convert similarly, with 0.3 equaling 30% by moving the decimal 2 places right and adding the symbol, or vice versa for reversal. Finding a percentage of a quantity involves multiplying the decimal equivalent by the whole, like 20% of 80 calculated as 0.2 times 80 yielding 16, applicable to discounts where a 20% reduction on $80 leaves 64 after subtracting 16. Percentage increase or decrease measures change relative to the original, where a rise from 100 to 120 is a 20% increase, found by dividing the difference by the original and multiplying by 100, or 20 over 100 times 100 equals 20%. Compound changes, like successive increases, are computed step by step or using multipliers, such as a 10% increase followed by 5% on 100 becoming 110, then 115.5, not simply 15% total due to the base shifting. Reverse percentages find originals from finals, such as if 120 is 120% of x, then equals 120 divided by 1.2, resulting in 100. In probability and statistics, percentages express likelihoods, like a 30% chance of rain meaning 30 out of 100 possible outcomes, or survey results where 45% of respondents agree, derived from the ratio of agreeing to total multiplied by 100. Financial applications include interest rates, where simple interest on 1,000 at 5% annually adds 50 each year, calculated as principal times rate times time over 100, while compound interest uses the formula principal times 1 plus rate over 100 to the power of time, growing exponentially. Ratios and percentages interconnect with fractions and decimals seamlessly, where a ratio of 3 to 5 equals 60% by converting to 3/5, then 0.6 times 100. In geometry, scale ratios like 1 to 50 mean 1 unit on a map represents 50 in reality, so a 3-unit distance scales to 150 units actual. Trigonometric ratios like sine as opposite over hypotenuse yield decimals or percentages for angles. Educational methods introduce ratios through visual aids like tape diagrams, dividing a strip into parts to show proportions, or pie charts for percentages depicting sectors as parts of the whole. Activities involve comparing recipes or analyzing data, such as sports statistics, where batting averages are ratios expressed as decimals but convertible to percentages by multiplying by 100, like 0.300 becoming 30%, though actually 300% in misinterpretation, highlighting the need for careful context. Challenges arise in misconceptions, like confusing percentage points with percent change, where a rise from 10% to 12% is 2 percentage points, but a 20% increase, clarified by distinguishing absolute versus relative. Word problems require identifying the whole, as in what percent of 40 is 8, solved as 8 over 40 times 100 equals 20%, or 8 is 20% of what, as 8 over 0.2 equals 40. Advanced extensions include continued ratios in chains, or using proportions in similar figures, where corresponding sides maintain the same ratio, allowing side lengths to be found by setting up equations. In business, profit margins as percentages of cost or sales guide decisions, while in science, concentrations like solutions at 10% by mass mean 10 grams solute per 100 grams solution. This study of percentages and ratios reveals their pervasive role in quantifying relations, each calculation a step in harmonizing parts with wholes, bridging arithmetic to real-world utility in finance, science, and daily decisions. Their elegance lies in simplicity, transforming complex comparisons into accessible figures, fostering a deeper appreciation for proportional reasoning in a measured, contemplative manner. Algebra and variables, a deliberate introduction to symbolic reasoning. Algebra and variables, within the realm of beginner mathematical principles, establish a framework for representing unknown quantities and relationships through symbols, allowing for the generalization of arithmetic operations into more abstract forms that can be manipulated to solve problems systematically. These concepts are unfolded progressively, starting from the substitution of letters for numbers in simple expressions, and advancing to the formulation and resolution of equations that model real-world scenarios, each step taken with a measured pace to ensure clarity and retention. A variable is essentially a symbol, often a letter such as X or Y, that stands in place of an unknown or changeable value, much like a placeholder in a sentence that can be filled with different numbers depending on the context. For instance, in the expression 2 times x plus 3, where might represent the number of items in a set. Expressions in algebra combine variables, numbers, and operations without an equality sign, serving as building blocks, such as 3y minus 4, which can be evaluated by substituting a value for y. If y is 5, it becomes 15 minus 4 equals 11, demonstrating how variables allow for flexible computation across multiple instances. Terms within expressions are separated by addition or subtraction, like in 2x plus 5, where 2x and 5 are terms, and like terms, those with the same variable raised to the same power can be combined, such as 3x plus 2x equaling 5x, a process known as simplifying that reduces complexity while preserving equivalence. Coefficients are the numerical factors multiplying variables, like the 3 and 3y, and constants are terms without variables, providing fixed values amid the variability. Equations introduce equality, setting two expressions equal, such as x plus 4 equals 7, asserting that the left side matches the right, and solving involves isolating the variable through inverse operations, subtracting 4 from both sides to find equals 3, maintaining balance as if on a scale where actions must be applied equally to both pans. The addition property of equality permits adding the same number to both sides without changing the solution set. Similarly for subtraction, multiplication, and division, except division by 0, which is undefined. Inequalities use symbols like greater than or less than, such as x minus 2 greater than 5, solved similarly but with care when multiplying or dividing by negatives, which reverses the inequality direction. So multiplying x less than 3 by -1 yields greater than -3. Linear equations in one variable like 2x plus 1 equals 9 are solved by subtracting 1 to get 2x equals 8, then dividing by 2 for x equals 4, with solutions verifiable by substitution back into the original. Word problems translate to equations, where phrases like 3 more than a number become plus 3, and twice as much as 2x. So if twice a number plus 3 equals 11, it forms 2x plus 3 equals 11, solved to equals 4. Systems of equations involve multiple equations with multiple variables, such as x plus y equals 5 and x minus y equals 1, solved by addition to eliminate y, yielding 2x equals 6 so equals 3, then substituting to find y equals 2, or by substitution where one variable is expressed in terms of the other. Graphing linear equations on a coordinate plane with x horizontal and y vertical plots points satisfying the equation, like y equals 2x plus 1, where for x0 y is 1, for x1 y is 3, connecting to form a straight line with slope 2, rise over run, and y-intercept 1. The slope-intercept form y equals mx plus b encapsulates this, where m is slope and b intercept, allowing prediction of values along the line. Parallel lines share slopes but differ in intercepts, while perpendiculars have negative reciprocal slopes, like 1/2 and -2. Functions formalize input-output relationships, denoted f of x equals expression, such as f x equals x squared minus 2, where input 3 output 7, viewed as machines processing numbers. Domain is possible inputs, range outputs, and functional notation aids in composition, like f g x, where gx is fed into f quadratic functions, like y equals x squared, graph as parabolas, symmetric curves opening up or down based on the coefficient sign, with vertex at the minimum or maximum point. Factoring decomposes expressions, such as x squared plus 5x plus 6 into x plus 2, x plus 3, verified by FOIL, first, outer, inner, last terms multiplying to original. This aids in solving quadratics set to 0, like x squared plus 5x plus 6 equals 0, yielding roots -2 and -3 where factors 0. The quadratic formula equals -b plus or minus square root of b squared minus for a c over 2 a solves generally. For a x squared plus bx plus c equals 0, providing roots even when factoring is complex. Polynomials are sums of terms with non-negative integer exponents, classified by degree. The highest exponent, like cubic for degree 3. Operations add like terms, subtract by distributing negative, multiply using distributive property across each term. Rational expressions, fractions with polynomials, simplify by canceling common factors, add by common denominators, much like numerical fractions. Matrices organize numbers in rows and columns, adding by corresponding elements, multiplying by row-column dot products, useful in systems solving via inverses. Determinants and inverses extend this, but at beginner levels, focus on basic operations. Algebraic modeling applies to rates, like distance equals rate times time, solving for unknowns in physics or economics, such as if traveling at 40 miles per hour for hours covers 100 miles, then 40x equals 100, x equals 2.5. Patterns and sequences use variables, arithmetic as a n equals a 1 plus, n minus 1 d, geometric a n equals a 1 times r to the n minus 1. Historical roots trace to ancient Babylonians solving quadratics, al-Khwarizmi's al-Jabr, meaning restoration, evolving to symbolic notation. Educational strategies use manipulatives like algebra tiles for visuals, balancing scales for equations, graphing software for lines. Common pitfalls include sign errors in distribution, like negative x minus 2 is negative x plus 2, or forgetting to flip inequalities with negatives. Practice reinforces, starting simple, building to complex. This introduction to algebra and variables illuminates their power in abstraction, each symbol a gateway to generalization, interconnecting with arithmetic and geometry in a tapestry of logical exploration, quietly enabling the modeling of the universe's patterns. Geometry and shapes, a tranquil survey of spatial forms. Geometry and shapes, as core elements of mathematical study, encompass the properties, measurements, and relationships of points, lines, and figures in space, providing a systematic way to describe the physical world through abstraction and precision. These principles are revealed layer by layer, commencing with the most elemental components like points and lines, and extending to complex configurations of polygons and solids, each aspect examined with a deliberate focus to illuminate their inherent structures without haste. A point is defined as a location in space with no dimensions, no length, width, or height, serving merely as a marker, such as the tip of a pencil or a star in the sky, from which all other geometric entities originate. Lines extend infinitely in both directions from points, possessing length but no width or thickness, and are classified as straight when they maintain a constant direction, like the horizon or a taut string, or curved when they bend smoothly, such as the arc of a rainbow. Line segments are finite portions of lines, connecting two endpoints with a definite length, while rays begin at a point and extend infinitely in one direction, akin to a beam of light emanating from a source. Parallel lines run alongside each other at a constant distance, never intersecting, as seen in railroad tracks, whereas perpendicular lines meet at right angles, forming 90 degrees, like the corners of a room. Transversals cross two or more lines, creating corresponding angles that are equal if the lines are parallel, a property used to prove parallelism in diagrams. Angles form where two rays or lines share a common endpoint, measured in degrees with a full circle equaling 360 degrees, a half turn 180, and a quarter 90. Acute angles are less than 90 degrees, sharp and narrow, obtuse greater than 90 but less than 180, broader in span and reflex exceeding 180, wrapping around. Complementary angles sum to 90 degrees, supplementary to 180, aiding in solving for unknowns when adjacent. In triangles, interior angles always total 180 degrees, a fundamental theorem derived from drawing a parallel line through one vertex and comparing alternate angles, ensuring consistency across all planar triangles. Triangles, three-sided polygons, are classified by sides: equilateral with all equal, isosceles with two equal, scalene with none, or by angles, right with 190 degree, acute all less, obtuse one greater. The Pythagorean theorem applies to right triangles, stating the square of the hypotenuse equals the sum of squares of the other sides, such as 3 squared plus 4 squared equals 9 plus 16 equals 25 equals 5 squared, solvable for any side by rearranging, like finding the hypotenuse as square root of a squared plus b squared. Congruence in triangles is established by criteria like side-side-side, where matching sides imply identical shapes, or side-angle-side, angle-side-angle, allowing proof without measuring all parts. Quadrilaterals, four-sided figures, include parallelograms with opposite sides parallel and equal, rectangles with right angles, rhombuses with all sides equal, squares combining both rectangle and rhombus properties, and trapezoids with at least one pair parallel. Properties include opposite angles equal in parallelograms, diagonals bisecting each other, and in rectangles, diagonals equal in length. The sum of interior angles in any quadrilateral is 360 degrees, derivable from dividing into two triangles, each contributing 180. Polygons extend beyond, with pentagons 5 sides, hexagons 6, heptagons 7, octagons 8, each regular when sides and angles equal, irregular otherwise. The interior angle sum for an n-sided polygon is n-2 times 180 degrees, so for a pentagon, 3 times 180 equals 540, averaged per angle in regulars. Exterior angles sum to 360 degrees regardless of sides, one per vertex turning to complete the shape. Circles are sets of points equidistant from a center, with radius the distance to the edge, diameter twice that through the center, circumference the perimeter as 2 pi radius or pi diameter, where pi approximates 3.14. Area is pi radius squared, encapsulating the space within. Chords connect points on the circle, arcs the curved portions, sectors pi slices with area fractional of the whole based on central angle over 360 times pi r squared. Tangents touch at one point, perpendicular to the radius there. Secants intersect at 2. Transformations alter shapes. Translations slide without rotation. Rotations turn around a point by degrees. Reflections flip over a line like mirrors. Dilations scale from a center by a factor, enlarging or shrinking proportionally. Congruence preserves size and shape through rigid motions. Translations, rotations, reflections. While similarity maintains shape but alters size via dilations, with corresponding angles equal and sides proportional. Coordinate geometry places shapes on a plane with x and y axes intersecting at origin 0, 0, points as ordered pairs x, y. Lines graphed by equations like y equals mx plus b, where m slope b y-intercept. Distance between points x1, y1, and x2, y2 is square root of x2 minus x1 squared plus y2 minus y1 squared midpoint average of coordinates. Shapes are plotted, like triangles, by connecting vertices. Areas calculated via formulas or shoelace method listing coordinates cyclically and summing products. Three-dimensional geometry introduces solids. Prisms with parallel bases like rectangular or triangular, volume base area times height, surface area sum of faces. Pyramids taper to apex, volume 1/3 base area times height. Cylinders as circular prisms, volume pi r squared h. Spheres all points equidistant from center, volume 4/3 pi r cubed, surface 4 pi r squared. Cones 1/3 pi r squared h, like pyramids with circular base. Measurement in geometry includes perimeter summing sides, area covering surface, triangle half base height, parallelogram base height, trapezoid average bases times height. Volume for capacity as mentioned. Units standardized like square meters for area, cubic for volume, conversions via factors. Symmetry appears in lines dividing shapes mirror equally, rotational turning onto itself. Tessellations tile planes without gaps, like hexagons or squares. Historical foundations from Euclid's elements axiomatizing points, lines, postulates like unique line through 2 points, proofs deductive. Applications in architecture designing stable structures, art perspective, navigation coordinates. Educational visuals use grids, compasses for circles, protractors angles, building models for solids. Common errors misidentifying classifications or formula misapplications, rectified by verification. This survey of geometry and shapes unveils their elegance in describing space, each form a building block in understanding the universe's architecture, interconnecting with algebra and coordinates, arithmetic and measurements, quietly fostering spatial intuition. Measurement and units, a measured approach to quantifying attributes. Measurement and units, as essential principles in mathematics, involve the assignment of numerical values to physical attributes such as length, weight, volume, time, and temperature, utilizing standardized systems to ensure consistency and comparability across observations and calculations. These concepts are introduced in a structured manner, beginning with the basic act of comparing objects directly and progressing to the use of precise tools and conversion methods that allow for accurate quantification in diverse contexts, each step fostering an appreciation for the order imposed on the tangible world. Direct comparison serves as the foundational method, where attributes are assessed without numbers, such as determining which of two sticks is longer by placing them side by side, or which container holds more by pouring liquid from one to the other until overflow indicates capacity difference, emphasizing relative qualities before numerical assignment. Standard units are established to provide uniformity, drawing from systems like the metric, based on powers of 10 for ease of conversion, or the imperial, rooted in historical precedents like the foot or pound. In the metric system, length is measured in meters, with prefixes like kilo for thousand, centi for hundredth, milli for thousandth. So 1 kilometer equals 1,000 meters, 1 centimeter 1/100th of a meter, facilitating mental shifts by moving decimal points. Converting 2.5 kilometers to meters involves multiplying by 1,000 to get 2,500. Mass uses grams, volume liters, where 1 liter equals 1,000 cubic centimeters, linking linear measures to capacity through geometry, as a cube 10 centimeters on each side holds 1 liter. Imperial units include inches, feet, yards for length, 12 inches per foot, 3 feet per yard, 1,760 yards per mile, and ounces, pounds for weight, with 16 ounces per pound. Conversions between systems require factors, like 1 inch approximately 2.54 centimeters, applied multiplicatively, such as converting 6 feet to meters by first to inches, 72, then multiplying by 0.0254 to get about 1.83 meters, or using direct factors like 0.3048 meters per foot times 6 equals 1.8288. Tools for measurement enhance precision. Rulers or tape measures for length, marked in units for direct reading. Scales for mass, balancing against known weights or digital displays. Graduated cylinders for volume, reading meniscus levels. Clocks for time, dividing seconds, minutes, hours. 60 seconds per minute, 60 minutes per hour, 24 hours per day. Thermometers for temperature in Celsius, where water freezes at 0, boils at 100, or Fahrenheit, freezing at 32, boiling at 212. Accuracy depends on tool calibration and user technique, avoiding parallax errors in readings by viewing perpendicularly, and considering significant figures to reflect precision, like measuring to the nearest millimeter rather than assuming infinite detail. Perimeter, area, and volume extend measurement to shapes. Perimeter sums lengths of boundaries, like a rectangle 10 by 6 with perimeter 2 times 10 plus 6 equals 32 units. Area quantifies surface, rectangle length times width equals 60 square units, triangle half base times height, circle pi radius squared. Units are squared for area such as square meters, emphasizing two-dimensional coverage. Volume for three-dimensional, cubic units. Rectangular prism length times width times height. Cylinder pi radius squared height. Sphere 4/3 pi radius cubed. Applied in contexts like calculating room paint needs from wall areas or tank capacities from volumes. Time measurement involves intervals, elapsed as end minus start, like a task from 9 a.m. to 11:30 a.m. lasting 2 hours 30 minutes, convertible to minutes as 150. Speed derives from distance over time, like 60 kilometers in 2 hours equaling 30 kilometers per hour, a rate linking measurements. Density, mass over volume, like 1 gram per cubic centimeter for water, useful in material identification. Conversions within and between systems use proportions or unit factors. To change grams to kilograms, divide by 1,000 since 1 kilogram equals 1,000 grams. For miles to kilometers, multiply by 1.609, as 1 mile approximates that. Dimensional analysis changes factors, canceling units, like converting 50 miles per hour to meters per second. 50 miles over 1 hour times 1.609 kilometers per mile times 1,000 meters per kilometer times 1 hour over 3,600 seconds, yielding about 22.35 meters per second. Estimation approximates measurements when exactness is unnecessary, rounding to nearest unit or using benchmarks, like a door about 2 meters high, for quick assessments, reducing error in planning. Error analysis considers absolute error as difference from true value, relative as that over true, percentage as relative times 100, minimizing through repeated trials or better instruments. Temperature scales convert via formulas. Celsius to Fahrenheit as C times 9/5 plus 32, Fahrenheit to Celsius F minus 32 times 5/9, Kelvin as Celsius plus 273.15, absolute zero at 0 Kelvin. These apply in science, like room temperature 20 Celsius equaling 68 Fahrenheit. Angles measure rotation in degrees or radians. Full circle 360 degrees or 2 pi radians. Pi radians 180 degrees, convertible by multiplying degrees by pi over 180. Protractors align for reading, essential in geometry. Capacity and weight interlink. Capacity for liquids in liters or gallons. 1 gallon about 3.785 liters. Weight for solids, though fluids have both, like water 1 kilogram per liter. Historical evolution from body parts, cubit elbow to fingertip, about 45 centimeters, to standardized like meter as 1/10,000th distance from equator to pole, now light distance in vacuum over time fraction. International System, SI, unifies base units meter, kilogram, second, ampere, Kelvin, mole, candela, derived like Newton for force. Educational progression starts non-standard units, like packing lengths with feet, advancing to standards, measuring objects, converting, problem-solving like fencing yards from perimeter. Activities include building scales, timing events, mapping rooms. Challenges: unit mix-ups causing errors like NASA Mars probe loss from pounds versus newtons, resolved by consistency checks. Advanced: uncertainty propagation in calculations, like adding measurements with errors. This exploration of measurement and units highlights their role in bridging abstract math to reality, each quantification a step in understanding scale, interconnecting with geometry and dimensions, algebra and formulas, arithmetic in computations, quietly enabling scientific and everyday precision. Data analysis and statistics, a gentle overview of patterns in information. Data analysis and statistics, as foundational principles in mathematics, involve the collection, organization, interpretation, and presentation of information to uncover patterns, trends, and insights that inform decisions in an orderly fashion. These concepts are approached methodically, starting from the simple gathering of raw data and advancing to the application of measures and visualizations that reveal underlying structures, each phase conducted with a steady progression to allow for clear comprehension without overwhelming detail. Data itself consists of facts or figures collected from observations, surveys, experiments, or records, categorized as qualitative, descriptive like colors or opinions, or quantitative, numerical like heights or temperatures, with discrete data in whole numbers such as counts of items, and continuous in any value like weights measured to decimals. The process begins with data collection, where methods ensure reliability, such as random sampling to avoid bias, selecting subsets representative of the whole population, like polling a random 100 from 1,000 to estimate preferences. Surveys use questionnaires with closed questions for quantifiable responses. Observations record behaviors directly. Experiments manipulate variables to test effects, like varying fertilizer amounts on plant growth and measuring heights. Ethical considerations guide this, maintaining anonymity and consent, preventing manipulation that could skew results toward predetermined outcomes. Organization follows, sorting data into manageable forms, like lists ordered ascendingly or tables with rows for cases and columns for variables, such as a spreadsheet tracking student scores with names in one column, math scores in another. Frequency distributions count occurrences, for example, how many students scored in ranges like 0 to 20, 21 to 40, creating tallies that highlight common values. Histograms visualize this for continuous data, bars representing frequency and intervals, while bar graphs suit categorical. Bars separated for clarity, line graphs connect points for trends over time, like temperature changes daily. Central tendency measures summarize data with a single representative value. The mean arithmetic average calculated by summing all values and dividing by count, such as scores 10, 15, 20 summing to 45 divided by 3 equals 15. Sensitive to extremes where an outlier like 50 skews it higher. The median middle value when ordered resists outliers. For odd counts like 9, 11, 13, the median is 11. For even like 10, 12, 14, 16, average the middle 2 as 13. The mode most frequent value like in 2, 3, 3. 4 the mode is 3, possibly bimodal if two values tie in frequency. Variability assesses spread. Range as maximum minus minimum, simple but outlier prone, like scores from 50 to 90 range 40. Interquartile range focuses on middle 50%, subtracting first quartile 25th percentile from third 75th, robust against extremes. Variance quantifies average squared deviation from mean. For population dividing by n, sample by n-1 for unbiased estimate steps. Find mean, subtract from each square sum, divide appropriately. Standard deviation, square root of variance in original units, indicating typical distance from mean, like a low value suggesting clustered data. Probability distributions model data, normal as bell-shaped symmetric around mean, with 68% within one standard deviation, 95 within two. Skewness describes asymmetry, positive with tail right like income distributions, negative left. Kurtosis measures tailedness, high for peaked with heavy tails, low for flatter. Inferential statistics draw conclusions about populations from samples, using hypothesis testing. Null hypothesis assumes no effect, like mean equals known value, alternative opposes. Test statistics like T for small samples, Z for large, compared to critical values or p-values. Low p rejects null, indicating significance, commonly at 0.05 level, meaning 5% chance of error if rejecting. Confidence intervals estimate parameters, like 95% interval around sample mean plus minus margin of error, derived from standard error, Standard deviation over square root n times critical value. Correlation examines relationships between variables. Pearson coefficient from -1 to 1, positive for increasing together like height and weight, negative inverse like price and demand, 0 none. Calculation. Covariance average product of deviations over product of standard deviations. Causation requires more, like experiments controlling variables, as correlation alone misleads. Ice cream sales correlate with drownings, but heat causes both. Regression models relationships. Linear as y equals a plus bx, b slope from covariance over x variance. A intercept mean y minus b mean x predictions extrapolate, but caution beyond data range. Multiple regression includes several predictors, coefficients from solving equations. Data visualization enhances interpretation. Pie charts show parts of whole as percentages, best for few categories. Scatter plots points for two variables, revealing clusters or lines. Box plots display quartiles, median, whiskers for range, outliers as points. Heat maps color grids by value, useful for matrices like correlations. Outliers, anomalous points, detected via z-scores over 3 standard deviations or box plot rules, investigated for errors or genuine, potentially removed or winsorized by capping. Descriptive statistics summarize without inference, like sports averages or census demographics. Big data handles large volumes with computing, but basics apply. Historical roots in census for taxation, Gauss normal distribution, Pearson correlations. Applications in medicine testing drugs, business forecasting sales, social sciences polling. Education uses real datasets, like class heights for means, graphs, software like spreadsheets for calculations. Challenges. Sampling bias, like voluntary surveys attracting extremes, misinterpreted p-values as effect size, over-reliance on means ignoring distributions. Advanced. Bayesian incorporates priors, non-parametric for non-normal, machine learning for patterns. This overview of data analysis and statistics illustrates their utility in distilling information. Each metric a tool for clarity, linking to probability in inference, algebra and formulas, measurement in data, quietly empowering evidence-based understanding in a variable world. Probability and chance, a serene examination of uncertainty. Probability and chance represent essential aspects of mathematical thinking at the beginner level. They provide a way to measure the likelihood of events in situations filled with uncertainty. These principles are developed step by step. The development starts with basic ideas about possible outcomes and moves toward more detailed frameworks involving multiple events and distributions. Each part of this exploration contributes to a broader view of how mathematics can make sense of randomness in the world around us. Events are occurrences that might happen or might not happen. Examples include flipping a coin to get heads or picking a certain card from a deck. Probability gives a number to show how likely an event is. This number ranges from 0, when something cannot happen at all, to 1, when it is sure to happen. Values in between come as fractions, decimals, or percentages. For example, the chance of getting tails on a fair coin flip is 1/2 or 50%. This basic scale helps people understand risks and possibilities in everyday decisions. Sample spaces list every possible result from an experiment. In a coin toss, the space includes heads and tails. For rolling a 6-sided die, it covers the numbers 1 through 6. Listing everything ensures that nothing is missed and that outcomes do not overlap. When outcomes are equally likely, Probability is found by dividing the number of favorable results by the total number. The chance of rolling a 4 on a die is 1 over 6. This simple division works because each face has the same odds. Beginners learn this through hands-on activities like tossing coins or drawing colored balls from a bag. These exercises show how theory matches real results over many tries. Complementary events look at what happens when something does not occur. If the probability of drawing a red card is 1/2, then not red is also 1/2. Subtracting from 1 gives this value quickly. It saves time when counting the unwanted outcomes would take longer. Mutually exclusive events cannot both happen at the same time. Drawing an ace or a king from a deck fits this because one card cannot be both. Their probabilities add up directly. The chance of ace is 4 over 52, king the same, so together 8 over 52 or 2 over 13. When events can overlap, addition needs adjustment. The inclusion-exclusion principle adds the individuals and subtracts the shared part. This keeps the total accurate. Independent events stand alone without one affecting the other. Flipping a coin twice shows this. The first result does not change the second. Probabilities multiply for both happening. 2 heads in a row is 1/2 times 1/2 or 1/4. This rule applies to many separate trials. Dependent events change based on what came before. Drawing 2 cards without putting the first back makes the second draw rely on the first. If the first is an ace, then 3 aces remain in 51 cards. Conditional probability calculates this as the chance of the second given the first. It divides the joint probability by the given event's probability. Formulas like this help in step-by-step breakdowns. Tree diagrams map out possibilities with branches. Each branch shows an outcome and its probability. Paths multiply along the way to find combined chances. The ends sum up for overall probabilities. This visual tool clarifies multi-step processes like choosing outfits with different colors and styles. Bayes' theorem flips conditions around. It finds the probability of a cause given an effect. Doctors use it for test results updating disease odds. At beginner stages, it starts with simple examples like weather predictions based on clouds. Permutations count arrangements where order counts. Seating 4 friends at a table has 24 ways. This comes from 4 factorial, multiplying down from 4 to 1. The general formula for selecting r from n is n factorial over n minus r factorial. Combinations ignore order. Choosing 3 fruits from 5 without caring which comes first uses n choose r. This equals permutations divided by r factorial. Lotteries rely on combinations for huge odds. Understanding this shows why winning is rare. Binomial settings have fixed trials with 2 outcomes each. Success probability stays constant. The formula gives chances for exactly k successes in n trials. It multiplies combinations of n choose k by p to k times 1 minus p to n minus k for 5 coin flips getting exactly 3 heads. It is 10 times 1/2 to the 5th or 10 over 32. Expected values average outcomes weighted by probabilities. In a game winning $3 with probability 1/3 and 0 otherwise, expected is $1. This helps judge fairness over time. Random variables link outcomes to numbers. Discrete ones have countable values like die rolls. Continuous cover ranges like heights. Distributions show probabilities for each. Normal curves are symmetric bells. Most data clusters near the mean. About 68% falls within one standard deviation. Z-scores standardize by subtracting mean and dividing by deviation. Tables then give areas under the curve for probabilities. Large numbers law says results average to expected over many trials. flips near 50% heads with thousands of tosses. Central limit makes sample means normal for big groups. This underpins surveys estimating populations. Simulations mimic reality with random numbers. Computers generate trials to approximate hard problems. Estimating pi drops points in a square and counts inside a circle. Ratios converge to pi over 4. Applications cover weather forecasts with percentages or insurance setting rates on accident chances. Games teach through dice and cards. Paradoxes challenge intuition. Birthday sharing hits 50% with 23 people. Calculations show 1 minus all unique probabilities. History includes Pascal and Fermat solving gambling puzzles. Kolmogorov set axioms defining probability spaces. Education uses spinners and bags for experiments. Tallies approach theoretical values. Missteps confuse odds with probability. Odds are success to failure ratios. 1-to-1 means even chance. Base rates get ignored in conditionals. Tests seem accurate, but low disease prevalence skews positives. Further topics include Markov chains tracking states. They predict weather sequences. Quantum adds wave functions. Yet beginners focus on basics building confidence in uncertainty. This look at probability and chance highlights their role in quantifying the unknown. Each idea links to counting in permutations, data in distributions, logic in conditions. They quietly prepare for a world where not everything is certain, but patterns in chance emerge nonetheless. Patterns, sequences, and logic, a peaceful delve into structured thinking. Patterns, sequences, and logic form a harmonious trio in beginner mathematics. They guide the recognition of order amid apparent chaos and enable the prediction of future elements based on established rules. These principles are explored in a deliberate sequence. The exploration begins with identifying simple repetitions and advances to formal logical reasoning. Each component contributes to a deeper appreciation of how mathematics mirrors the predictable aspects of nature and thought. Patterns appear as recurring arrangements in numbers, shapes, or events. They invite observation and extension without demand for immediate complexity. For instance, a pattern like red, blue suggests the next color is red. This repetition fosters an intuitive sense of continuity. In numerical terms, a pattern such as 2, 4, 6, 8 reveals even numbers increasing by 2 each time. This allows one to forecast the next as 10. Such patterns are found in everyday life. They show up in the petals of flowers arranged in spirals or the stripes on a zebra. Mathematical patterns encourage the mind to seek underlying rules. This process builds a foundation for more abstract concepts. Visual patterns extend this idea through geometry. Tiles on a floor might alternate in color or shape to create a mosaic that repeats across the surface. Symmetry serves as a type of pattern. It divides a figure into mirror images along a line or point. For example, a butterfly's wings display bilateral symmetry. Each side matches the other perfectly. Rotational symmetry occurs when a shape looks the same after turning by a certain angle. A starfish exemplifies this with arms radiating equally from the center. These patterns are analyzed by counting repetitions or measuring angles. They reveal how transformations like reflections or rotations preserve the overall design. In art and architecture, patterns ensure balance and aesthetic appeal. They draw from mathematical precision to achieve harmony. Sequences take patterns further by ordering elements according to a specific rule. They create a list where each term depends on the previous ones. Arithmetic sequences add a constant difference to each term. Consider the sequence 1, 3, 5, 7. Here, the common difference is 2. To find the nth term, use the formula first term plus n minus 1 times difference. For the 10th term, it would be 1 plus 9 times 2, equaling 19. This formula derives from observing the pattern and generalizing it. Geometric sequences multiply by a constant ratio instead. For example, 2, 6, 18, 54 multiplies by 3 each time. The nth term is first term times ratio raised to n minus 1. So the fifth term is 2 times 3 to the fourth, or 2 times 81, resulting in 162. These sequences model growth or decay. Populations might follow geometric patterns if doubling periodically. Savings with interest accumulate similarly over time. Infinite sequences continue without end. They approach limits in some cases. The sequence 1, 1/2, 1/3, 1/4 diminishes toward 0. Convergent sequences like this sum to finite values in series. The harmonic series sums these reciprocals but diverges slowly to infinity. Fibonacci sequence stands out as a special case. It starts with 0, 1, then each term sums the two preceding. 1, 2, 3, 5, 8, 13, and so on. This appears in nature. Pinecones and sunflowers display spirals matching Fibonacci numbers. The ratio of consecutive terms nears the golden ratio, approximately 1.618. This irrational number symbolizes proportion in art and design. Sequences like this connect mathematics to biology and aesthetics. They show how simple rules generate complexity. Recursion defines sequences where terms rely on prior ones explicitly. The factorial sequence, where n factorial equals n times n minus 1 factorial, exemplifies this. It builds factorials like 1, 2, 6, 24 for 1 through 4. Recursive thinking applies to algorithms and computing. It solves problems by breaking them into smaller identical subproblems. Patterns in sequences often reveal recursive relations. This leads to closed-form expressions for efficiency in calculations. Logic provides the reasoning tools to validate patterns and sequences. It distinguishes true from false statements through structured arguments. Propositions are basic declarative sentences. They are either true or false, like 2 plus 2 equals 4 being true. Compound statements connect propositions with words like and or not. Conjunction and requires both true. Disjunction or needs at least one true. Negation not reverses truth value. Truth tables list all possibilities. For P and Q, the table shows P and Q true only when both are. This systematic approach ensures no ambiguities in evaluation. Conditional statements, if P then Q, imply Q follows from P. They are false only when P true but Q false. Biconditionals, if and only if, require both directions. Logical equivalence means statements with identical truth tables, like not P or Q, equaling not P and not Q by De Morgan's laws. These laws aid simplification. Proofs use logic to establish truths. Direct proofs assume premises and deduce conclusions. Indirect assume negation and find contradiction. Induction proves for all natural numbers. Base case checks first. Inductive step assumes for k and shows for k plus 1. This suits sequences. Proving the sum of first n naturals as n plus 1/2 uses induction seamlessly. Sets underpin logic with collections of elements. Union combines, intersection overlaps. Subsets contain within. Venn diagrams illustrate relations visually. Circles overlap for shared elements. Logic extends to quantifiers. Universal for all claims every instance. Existential, there exists needs at least one. Fallacies arise from flawed reasoning. Ad hominem attacks person not argument. Circular begs question. Avoiding these ensures sound conclusions. Boolean algebra formalizes logic with variables true or false. Operations mirror and or not. Circuits use this for computing. Gates perform operations. Patterns in truth tables reveal efficiencies. Applications span puzzles like Sudoku relying on logical deduction. Each row, column, block unique numbers. Cryptography uses sequences and logic for codes. Games like chess anticipate sequences of moves logically. Historical figures shape these. Aristotle's syllogisms, Boole algebra, Turing computation. Education builds with puzzles spotting patterns, extending sequences, constructing proof simply. Challenges include overlooking exceptions in patterns or confusing correlation with logical causation. Practice refines discernment. This delve into patterns, sequences, and logic highlights their interplay. Each fosters predictive and reasoned thinking. They interconnect with algebra and formulas, geometry and symmetries, probability in random sequences. They quietly cultivate a mind attuned to the world's ordered beauty.